So after discussion regarding the rate of reaction, so in today's class, we are going to start chemical equilibrium, like reversible reactions. Okay, reversible reactions, reversible reactions, reversible reactions. So basically, reversible reaction means you can say the reaction which can change from reactant to product and product to reactant, like forward and backward. Like I can say that this is bidirectional reaction. This is bidirectional reaction. Bidirectional means that the reactant can change into the product, okay, and the product can reverse back into the reactant side. This is called reversible reaction. So remember when the reactant, so remember when the reactant changes into the product, so we would say that this is we would say that this is a forward reaction. Okay, this is a forward reaction, right? And whenever the product will change into the reactant, okay, so then I would say that this is a backward reaction. Okay, this is a backward reaction. So basically these are the key terms, these are the key points regarding chemical equilibrium, like reversible reaction. So some reactions are irreversible reactions, like once the product is formed, so you can never convert them back. Like let's suppose you are going to make a tea. Once you have made tea, so this is irreversible reaction. Okay, you cannot be, you can say, convert like this reaction back to the reactants. So this is irreversible reaction. So like these, we have some reversible reactions as well. Like practically, if I say, let's suppose you have practically, let's suppose you people know that we have copper sulfate aqueous. We have copper sulfate aqueous, and this is copper sulfate solid. Remember, this means that this is hydrated. This is what? This is hydrated, and this is anhydrous. This is anhydrous. You know, anhydrous means there is no water. There is no water. This is dry. And hydrated means this is aqueous, like the water is attached, basically. So when water is attached, this is of blue color. And when this is anhydrous, this is of white color. Okay. So the formula for hydrated copper sulfate is copper sulfate dot 5H2O. Okay, copper sulfate dot 5H2O. I'm supposed to write just like that, dot 5H2O, dot 5H2O. That's why this is blue in color. Okay, so I am going to provide heat. I am going to provide heat to this aqueous copper sulfate. This is of blue color. So when you will provide heat, obviously up to the boiling point of water, obviously the water is attached to this copper sulfate. So the water will boil. So the water will boil. So the water will evaporate, leaving behind the copper sulfate. That is anhydrous copper sulfate. This is of white color. But now I'm thinking that I want to convert it back into the hydrated copper sulfate. So just add water, just add few drops of water. So you will see that the anhydrous copper sulfate, that is of white in color, it would be converted back into the blue color. And blue color is of, like you can say, this is hydrated copper sulfate. So basically these are the reactions which can change from reactant to product and from product to reactant. So this is the live example of like the reversible reaction. So this is simple experiment. You can do this experiment at your home as well, but you must have a copper sulfate. And you know, copper sulfate is the toxic, you can say, compound. So take, like, you can say, uh, safety protocols are required while you are dealing with copper sulfate. So this is an example of like how the reversible reaction like behaves. So in short, summarize, like they can change from reactant to product and from product to reactant. They have, like, they are bidirectional reaction, and reversible reactions are represented by double arrow. Okay, reversible reactions are represented by double arrow. So see this, see this is, and see this arrow. This is reversible. Okay, and this is irreversible, and this is irreversible. Okay, reversible and irreversible, right? And one thing that is very important in reversible reactions, that basically there is a term that is called, equilibrium. That is called equilibrium. Can anyone tell me, like, what is equilibrium? Can
When the
anyone tell
rate
me
of
what
the
is
forward
equilibrium?
and backward reactions are equal.
No, that was the dynamic equilibrium. I'm talking about the simple term that is equilibrium. So you know,
The
equilibrium means
concentration of the reactants and products is equal.
exactly like the amount of reactants are equal to the amount of product. Amount of reactants are equal to the amount of product. This is called simple equilibrium. Like, let's suppose I have a reaction. Let's suppose I'm considering this reaction that is called Haber process. This is very famous process, and I'm assuming that I have taken 100 kg of the whole reactant side, and the time is equal to 0 seconds. Obviously, the time can never be zero. Obviously, the time can never be zero. It means that the reaction has not started yet. Okay, so 0 kg product is formed. Obviously, man, the reaction has not started yet, so there is no product. Now I'm saying that reaction has started and 5 seconds have been passed. 5 seconds have been passed. 20 kg of the product is formed and 80 kg of the reactant is left. Then I'm saying that, then I'm saying that 10 seconds have been passed. Okay, 50 kg product is formed. Okay, and 50 kg, like in total, I'm talking about in total. So 50 kg reactant is left behind. So this is the point where the amount of reactant is equal to the amount of product. So I can say that this is called equilibrium. This is called equilibrium, just like a seesaw. Just like a seesaw. Let's suppose this is a plank, okay? And here A and here is B. 40 kg and 40 kg. So this is at equilibrium because they have the same masses. Same goes in the reactions. Same goes in the reactions, basically. Same goes in the reactions. So when the amount of reactants are equal to the amount of products, so I can say that the equilibrium is established. But remember, we are not interested in simple equilibrium. We are not interested in simple equilibrium. We are interested in dynamic equilibrium. We are interested in dynamic equilibrium. Dynamic, dynamic dynamic equilibrium. Okay, we are interested in dynamic equilibrium. So like I can say that let's suppose I have this tube just like that. Okay, I have this tube, right? H-shaped tube. Okay, and then I have filled this side. I have filled this side with water. I need your concentration right now. Let's suppose I have filled this side with water. Okay, this is side A. This is side A. Common sense, obviously, these are the water particles. These are the water particles. Okay, these are the water particles. These are the water particles. Okay, so the particles will start to move from the particles will start to move from A to B. The particles will start to move from A to B. So the time would come, you will see that after a time, like let's suppose after 5 seconds, 10 seconds, 15 seconds, 20 seconds, you will see just like that. 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 The particles have moved from left to right. Right now you can see, they have the same number of particles. Let's suppose, or you can consider in A side you have 75 atoms, and here you have only 50 atoms, or you can say water molecules. I need to make you understand something, so I need your concentration right now. So this is a molecule, okay? This is a molecule. Okay. It seems that it looks like that the particles are not moving. They are static. But in reality, they're not static. They are moving. They are moving right now. They are moving. But remember, the movement is very smooth. The movement is quite a smooth movement. So it seems that the particles are not going to move from left to right or right to left. But in reality, I'm saying that the particles are moving from left to right and the particles are moving from right to left. But you will not see the change in volume. You will not see, like you can say, uh, your left hand side is going to increase, or you will never see that your right hand side is going to increase, like the surface of the right hand side will increase. No, because the movement is very smooth. If you ask how, I would say that, let's suppose, just consider that the 5 molecules are moving from left to right. The 5 molecules are moving from left to right at the same time. At the same time, the 5 molecules are moving from right to left. At the same time, the 5 molecules are moving from right to left. So the movement is very smooth. The net amount will remain the same. The net amount would remain the same. So you will see, like it looks like that there is no change in particles. They are not moving, but I'm saying that the movement is very smooth, but it doesn't mean that they are not going to move. They are moving. This is called equilibrium. This is called equilibrium. When the particles are moving from left to right, this is called forward. This is called forward. And when they are moving from right to left, this is called backward. This is called backward. Simple. Okay. So when the rate is same, like the forward and the backward, when the rate of forward is equal to the rate of backward, then I can say that this is dynamic equilibrium. Then I can say that this is dynamic equilibrium. So remember, This is the dynamic equilibrium when the rate of forward reaction is equal to the rate of backward reaction. When the rate of forward reaction is equal to the rate of backward reaction. This is called dynamic equilibrium. Are you getting my point? Yes or no? Yes?
Yes.
Okay.
Yes, sir.
Amaya, do you understand this? Aryan. Who is Aryan? Aryan, this is your first
Hello.
class?
No,
Aryan,
hello.
yes, yes.
Yes, this is not my first time.
Okay. Oh, okay. Ibrahim, are you going to understand my points? Yes or no? Hamna, Liaquat, Fatma, are you getting my point?
Yes, sir.
Reni,
Yes,
Mahin,
sir.
Madarka, okay, Mohimin, Rija, yes.
Yes, sir.
Okay, good. So basically, if the examiner asks the definition of the dynamic equilibrium, so you would be writing when the rate of forward reaction is equal to the rate of backward reaction. Okay, when the rate of forward reaction is equal to the rate of backward reaction, just like that. Just like that. Rate of forward reaction is equal to the rate of backward reaction. This is called the dynamic equilibrium. Okay, one thing is very important regarding the dynamic equilibrium, okay, that we have certain conditions. We have certain conditions to attain, to have a dynamic equilibrium. We have some conditions, okay? So let me tell you what are the conditions. What are the conditions? What are the conditions for dynamic for dynamic equilibrium? What are the conditions for dynamic equilibrium? So remember, point number one, you must have you must have you must have a reversible reaction. You must have a reversible reaction. Okay, in irreversible reactions, only the reactants are going to change into the product side, so the products are not going to change into the reactant. So obviously this is irreversible reaction, so you will not see any type of dynamic equilibrium in that reaction. So that's why I'm saying that to attain a dynamic equilibrium, you must have a reversible reaction. Okay, and the next point for the dynamic equilibrium is that you must have a closed container. You must have a closed container. Okay, but why? Let's suppose I have this container. Let's suppose I have this container. Okay, in this container, these species are going to react together just like that, and they are going to form this. All are gases. All are gases. Okay, this is the reaction that's going to take place in this. That's going to take place in this container. Okay, so let's suppose once the ammonia is formed, once the ammonia gas is formed, if you can see this, once the ammonia gas is formed, so the ammonia gas will escape from the reaction mixture. The ammonia gas will escape from the reaction mixture. Okay, the ammonia gas will escape from the reaction mixture. Okay, so when the ammonia has escaped from the reaction mixture, when the ammonia has escaped from the reaction mixture, so then how the product will, you can say, reverse back into the reactant side? So then how the product will reverse back into the reactant side? Then how can I say that this is a reversible reaction? Then how can I say that this is a reversible reaction? So remember, your container must be closed so that nothing could escape from the container. Nothing could escape from the container. So you can achieve a dynamic equilibrium. So that's why I'm saying that you must have a closed container. Okay. So these are the conditions if you are going to have dynamic equilibrium. So you must have a reversible reaction. Obviously, in irreversible reaction, you will never see any type of equilibrium. And then you must have a closed container, because sometimes we are dealing with the gas. So when the gas will escape from the beaker, from the container, so which one will reverse back to the reactant side? And if nothing is converting back into the reactant side, so obviously I can never say that the rate of forward reaction is equal to the rate of backward reaction. So in that case, let's suppose I have this reaction. I'm taking it arbitrary, randomly. Let's suppose this is a reaction. Just consider this. Let's suppose this is a reaction, and this is going on in this reaction. And this is going on in this reaction. See the length of arrow. This is larger and this is smaller. It means that the rate of forward is higher, but the rate of backward is lower, because the length of the backward arrow is smaller. It's going to represent that the backward reaction is is at the lower extent, but the forward reaction is at higher extent. So remember, in perfectly reversible reaction, the length of both arrows would be the same. Okay, the length of both arrows would be the same. But if you ever see these type of things, so you must have an idea that this is not 100% reversible reaction. Okay, so remember, in dynamic equilibrium, the rate of forward reaction should be equal to the rate of backward reaction. And let me tell you one thing more. It's you can say misconcept. Some people, like I can say, like few, like most of the people like think that like if we are going to achieve a dynamic equilibrium, so the number of reactant particles must be equal to the number of product particles. But in reality, this is not so. It is not depending upon the number of particles. As I told you, here we have 75 molecules, and here we have 50 molecules. Okay, here we have 75 molecules, and here we have 50 molecules. Okay, but I told you that 5 molecules are going from left to right at the same time. 5 molecules are going back from right to left. Okay, the same particles, the net amount is same. This is called dynamic equilibrium. And let's suppose Madarka is saying that, sir, what if we have 100 particles and 100 particles? No problem. The 10 particles are going from left to right at the same time. 10 particles are going from right to left. This is dynamic equilibrium. So this is useless. It's not depending on the number of particles. It totally depends on how the rate is going on. How the rate of forward reaction is going on, and how the rate of backward reaction is going on. When the both rates are equal, then I will say that this is dynamic equilibrium. Yes, are you all getting my point? Yes or no? All clear? Aryan,
Yes.
Fatma, yes. Hamna, Ibrahim, Mahin, Mohaimin, Rija, yes.
Yes, sir.
Ayat, okay, good. Yes, Amaya, Anaika, is that clear? Abdul
Yes,
Wase,
clear.
Adan,
Yes.
Ayat Zubair. Okay, good.
Yes, sir.
So, so if I ask the definition of the dynamic equilibrium, so you are supposed to say the rate of forward reaction is equal to the rate of backward reaction. But, but, there is a problem. There is a problem. There is a problem. There is a problem. What? Basically, industrialist. Basically, industrialist, you know, they just do a small investment, okay, and they want a high yield. Like I'm using the word yield. Yield means amount of product. Yield means amount of product, okay. But unfortunately, if you are dealing with the reversible reactions, obviously they can never go to completion. This is also the characteristic of dynamic equilibrium. I can say that they can never, they can never go to completion. They can never go to completion. Why? Why? If you are thinking that, why the sir is saying that the reaction can never go to completion, so let me tell you something. As I told you before, that the like the reversible reactions are those reactions which can change from reactant to product and from product to reactant. Like, and let's suppose right now this is 100%. I need your concentration. I need your concentration. This is very important concept. Let's suppose right now we have 100% reactant. We have 100% reactant and we have 0% product. The reaction has not started yet. It's simple. And then I'm assuming that the reaction has been started. So this much product is formed. This much product is formed. This much product is formed, right? So once the product is formed, once the product is formed, even 5%, 6%, 4%, 2%, 1%, 8%, 9%, 7%. So remember, it will convert back to the reactant side. It will convert back to the reactant side. It will convert back to the reactant side. Okay, it will convert back to the reactant side. So the reactant will be changing into the product will be changing into the reactant will be changing into the product will be changing into the reactant side. So obviously I can say that the reaction will never go to completion. You will never see that the 100% product is going to form. No, never. They will not form 100% product. Why? Because this is a reversible reaction. The product is also going to the reactant side. So this is a big problem to the industrialist. They want 100% yield. They are having, you can say, the huge investment. Okay, after a huge investment, and they are just getting 40% product. Oh man, like 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 so disappointment, because they want a higher yield after having a good investment. They want good yield, they want good amount of product. But unfortunately, if the reaction is reversible, like I'm talking about the Haber process, Haber, basically it's the name of scientist who did, like, who had this reaction, ammonia, like the preparation of ammonia. So right now we have to solve this problem. We have to solve this problem. I mean to say that we want to achieve a good yield. We want to achieve a good yield. We want to achieve good amount of product. We want to achieve more and more product. So what am I supposed to do? What the conditions am I supposed to change? What am I supposed to do to increase the yield, to increase the amount of product? Okay, this is the problem that we are going to solve. This is the problem that we are going to solve to these reactions that are at dynamic equilibrium. Okay, like I told you, reactant can change into the product and the product can change into the reactant side. So obviously we are not going to have 100% product. So only 10 to 15 or 20% product is going to form in the dynamic equilibrium reactions. So there was a scientist named Lee Chatelier. There was a scientist named Lee Chatelier. You're not supposed to memorize the name. Okay, you're not supposed to memorize the name, but you must know what he did. So basically, let me write this. Like, what's the problem? Okay, industrialists like do a good investment and they want a higher product, a good amount of product. Okay, so unfortunately, reversible reactions do not give good yield. Reversible reactions do not give good yield. This is the problem. So to solve this problem, there was a scientist that was Lee Chatelier. Okay, that was Lee Chatelier. L E Chatelier. Chatelier. Lee Chatelier's principle. See this. I want to give you an idea.